In this video, I want to talk about how you represent straight lines and planes in three-dimensional space. In ordinary algebra, if I have 2 points in the plane, what we do is we measure how much the vertical coordinate changes divided by the horizontal. We call that the slope, and we use that as a number that tells me the direction of the straight line. There are many straight lines with the same slope, so you would have to particularly know that a given point, either P or Q here, were on the line, to pick out the one that you're interested in. In three-dimensional space, we have a lot more freedom to move around. A single number is not going to correctly describe the direction of a straight line. If I know 2 points on the line, though, I can form the vector from one of them to the other one, and this will describe the direction correctly for me. This is a vector. It's an arrow in 2 or 3-dimensional space. Observe that if I had one such direction vector, I could multiply it by 2, and I would still have a valid direction vector. If I were to multiply this vector by -1/2, it would point this way, which is still along the same straight line direction. So if I have one of these direction vectors, and it was convenient for me to multiply or divide it by any number that isn't 0, then that would be perfectly all right to do. If I pick a point on the straight line that is not point P, whose coordinates I'm going to call x0, y0, z0, call the coordinates of this other point just x, y, and z, representing some generic point on the straight line. If I form the vector from P to R, then this is a vector that connects 2 points on the straight line. This vector must point in the same straight line direction as the vector from P to Q, or V as I might call it. I'll make up letters to represent the components of a vector that is parallel to my straight line. For convenience, I'll just call them A, B, and C. So what I know is the vector from P to R must be a multiple of the vector from P to Q. P to R must be a multiple of this vector V. The thing I multiply V by to get the vector from P to R, I'll just call T. T is a number. It can be any value you care to make it. If I figure out the component form of the vector from P to R, as usual, we use our recipe end minus start. R has coordinates just generic letters x, y, and z. P has coordinates x0, y0, z0. Doing the end minus start thing, the components of the vector from P to R are these numbers. This must be a multiple T of vector V. I'm calling V A, B, C component-wise, so this vector must equal T multiplied by vector A, B, C, but we know how to multiply a number by a vector: T times A, T times B, and T times C. For 2 vectors to be equal, though, their components have to be equal. That means that this number must equal that number, this number must equal that one, and this one has to equal that one. I can split this vector equation up into 3 ordinary equations. Now, from there are 2 common forms that people use. We'll look at both of them. This form is the one more oftenly useful to us in our situations. We might refer to that as the parametric form of the equation for the line. If I give you something that looks like that, then the interpretation is these constant terms are the x, y, and z coordinates of a point on the line, and the things that I multiply the variable by, the things I multiply by t, the a, b, and c in this case, are the components of a vector in the same direction as the straight line. The second form, assuming that none of the numbers a, b, and c are 0, I could solve that equation and find out that t is the same number as x minus x0 divided by a. But looking at that equation, I'd find out that t is also y minus y0 divided by b, and doing likewise for the third equation, t is also z minus z0 over c. This is what people sometimes call the symmetric form for the straight line. Notice that this is not one single equation that says a combination of the variables is, say, some constant. This says that three separate things are equal to each other. For example, if I wrote these equations down in front of you and asked you what this represents, the correct answer is this is a straight line that passes through the point 5, 2, 3 and is in the direction of the vector 2, negative 1, 7. So when I write this out, I have to be very careful to use parentheses on that and square brackets on the other one. Or I could write the other one as 2i minus j plus 7k if I thought that was better. On the other hand, if somebody told me that x minus 2 over 3, y minus 4 over 5, and z minus 1 over 2 were all the same number, then I would interpret that as the symmetric form of the equations of a straight line. X minus x0, y minus y0, z minus z0. This straight line is going to pass through the point 2, 4, 1. The numbers on the bottoms of the fraction are the a, b, c numbers. These are the components of a vector along whose direction the straight line passes. So we can write the same kind of sentence for this situation as we did for that one. When you took college algebra, one problem that they gave you was, given 2 points on a straight line, find the equation for the line. We have a similar situation here in three-dimensional space. We're going to have 2 points, P, which has coordinates 1, 2, 3, and Q, 2, 5, 7, and I'd like to find the equations of a straight line that passes through those 2 points. Just as in college algebra, I've got to cook up something that tells me the direction of the straight line. Doing the usual n to minus star, I find that a vector that is parallel to the direction of the line is 1, 3, 4. I can write down, using point P for my reference point, x is 1 plus 1 times t, y is 2 plus 3 times t, and z is 3 plus 4 times t. It's worth mentioning that I could have picked the other point to use as my representative point. Then I would have gotten different looking equations. The direction vector that I'll use will still be 1, 3, and 4, so the coefficients of the variable in my new set of equations will be 1, 3, and 4, just as previously, but this time my known point is x equals 2, y equals 5, z equals 7, so I write those in instead. These equations don't look the same, but actually are the same. I'm going to look at different scenarios in both of these two situations. In the first set of equations, if I set t equal to 0, I find out that the point where x is 1, y is 2, and z is 3 is a point of the straight line, which makes perfect sense as that's the point we used to build those equations. In the second set of equations, if I make t equal to 0, x will be 2, y will be 5, and z will be 7, which gives me point Q. This points out an important fact. I've got a letter t in this set of equations, which for a given value of t, I get a given value of x, y, z numbers for the first straight line. Here, a given value of t doesn't mean the same thing. This is going to give me x, y's, and z's that are on the second straight line if I think that these are maybe not the same. So t being 0 here gives me different results from t being 0 there, even though these are supposed to be the same straight line. So what I'm going to do is I'm going to try to figure out if this point, x equal 2, y equal 5, z equals 7, is on that straight line. I'm going to try to figure out whether or not x equal 1, y equal 2, z equal 3 is on that straight line. And if both of those things are true, then these actually do represent the same straight line, because as we know, given 2 points, there's only one straight line that passes through them. I want to try to find a t number so that when I stick that t number into these 3 equations, I get x equal 2, y equal 5, and z equal 3. If I think about what that would mean, 1 plus t, the x-coordinate, would have to come up equal to 2. 2 plus 3t, the y-coordinate, would have to come up equal to 5. And 3 plus 4t would have to come up equal to 7. We have 3 equations that need to be satisfied, but we have only one variable. Usually, such a thing is not going to have any solutions at all, but if you look at the first one, 1 plus t equals 2 says that t should be 1. 2 plus 3t equals 5 means that 3t should equal 3, and that says t is 1. 3 plus 4t is 7, says that 4t should be 4, t should be 1. By good luck, there is a t number that will work here. When t is 1, x will be 1 plus 1, which is 2, which is what I want it to be. When t is equal to 1, y will be 2 plus 3 times 1, which is 5, and 3 plus 4 times 1 is 7. So we already knew that x equal 1, y equal 2, z equal 3 is a point of this straight line, but we now know that x equal 2, y equal 5, z equal 7 is a point of this straight line as well. Conversely, we already know that x equal 2, y equal 5, z equal 7 is a point of this straight line. I want to figure out whether or not the point x equal 1, y equal 2, z equal 3 is a point of that straight line or not. Doing the same kind of arithmetic, I find out that if t is negative 1 for this second set of equations, everything will work out fine. X will be 2 plus negative 1, which is 1. Y will be 5 plus negative 3, 5 minus 3, which is 2. And z will be 7 plus negative 4, which is 3, which gives me back this point on the other line. So this point is on both straight lines. that point is on both straight lines. The lines described by these two sets of equations are actually the same straight line. It may be a little bit disturbing that t has to be both 1 and -1, but we're comparing apples and oranges here. T is the number I stick into this set of equations to get a point on the first line. That should be pushed off on the side and ignored for a moment. If t is the number that I stick into these equations, what comes out is not points on the first line, but points on the second line. I could have used any letter other than t here that I wanted to, and in point of fact, that's what we're going to start doing. If I have two straight lines running around, I'm going to use different letters for the parameter. I'll probably still call one of them t, and I'll call the other one lowercase script s or something, or some other letter, just to make sure that I don't confuse these t values with those t values. Another point worth mentioning is, in two-dimensional space, if two straight lines are not parallel, then they intersect someplace. That isn't true in three-dimensional space. Imagine that you have a cube, and along one edge of the cube you draw a straight line, and then along one face of the cube that never touches this face or that face, you draw a straight line like this. Those two straight lines are not parallel, and yet they never touch each other either. This is an example of what's called a pair of skew lines. So the issue of whether or not two lines intersect is not as simple as are they parallel or not. As an example of this, I'd like to think about the straight line described by this first set of equations and that described by the second. As I said previously, I want to use different letters for the parameter, otherwise I'll confuse myself. So I'm going to use t for the parameter here, and lowercase script cursive s for the parameter here. I don't want to use the printed s because it looks too much like a 5. I want to decide if these two straight lines intersect any place. If they do, that means that there's a t value, so that when I put that t value into these three equations, I get an x, a y, and a z, and that x, y, z is also a point of the second line, so there must be an s number that I could put into these three equations and get the same x, y, and z that I got from the first set. To make that happen, it must be true that the x-coordinates that come out of the two sets of equations are the same, and the y's, and the z's. All three of these things have to be true if I'm going to have an intersection point. I have a set of equations here. I have three equations, but only two variables. Usually, if you just write down equations of that nature, you don't get any solution at all. There is no t and s that make all three of these equations true. For a given particular situation, you might have a solution. We don't know at this stage, so we have to try to see if there are any t numbers and s numbers that obey all three of these equations. In order to get the same point on the two straight lines, it's necessary that these equations be true. The x, the y, and the z coordinates have to match up. Now, I only have two variables, but I have three equations. I have three requirements that I want to be true. Usually, this means it's not going to work out, but then again, maybe it will. We won't know until we find a solution to this system of equations, or somehow determine that there isn't any. I'm going to rewrite my equations this way. If you'll notice, in the first equation, s shows up as a term plus 4s, and that's how the third equation is as well. So what I'm going to do is I'm going to subtract the first equation away from the third one. 4t minus 2t is 6 plus 4s minus 4 plus 4s. The reason I decided to do that is this will make the 4 times s terms go away. Doing the arithmetic, if this is going to work, if I'm going to find an intersection point, I totally know that t has to be 1 now. But I still have some issues here. T is supposed to be 1, so in my equations, if you set t equal to 1, you still have 3 equations that are supposed to determine what s is. If all 3 of those give the same answer, then we're in business. We have a point of intersection. But if one of them says, say, that s needs to be 8, while another says s needs to be 10, then there'd be no way to make all of these equations true, and we will not have a point of intersection. Seeing what happens in these equations when t is 1, I find out that 2 needs to equal 4 plus 4s. That means that negative 2 should equal 4 times s. S should be negative 2 divided by 4. This says that s needs to be negative 1/2, if this is going to work out correctly. This equation says that 3 needs to equal 8 plus 10s, negative 5 needs to equal 10 times s needs to equal negative 5 divided by 10, s needs to be negative 1/2. If t is equal to 1 and s is equal to negative 1/2, the first 2 equations are true. The only thing that could go wrong is if that third equation said something different than s equals negative 1/2, but 4 minus 6 is negative 2, negative 2 over 4. The third equation says that s is equal to negative 1/2. You can check this if you want, but if the arithmetic is correct, if I take t equal 1 and put it into these equations, I'll get a certain point, x, y, z. If I take s equals negative 1/2 and put it into those equations, I'll get the same point, and that will be the intersection point to the 2 straight lines. It turns out that the intersection point is at x equal 1, y equal 2, z equal 3. In an effort to keep these things short, I'm going to stop there again. In the next video, we'll have a discussion of how to describe planes in 3-dimensional space. Until then, I hope everybody has a good day. I'll talk to you again soon.